Lecture 18 is our second lecture on modern theory of solids. In this lecture, we talk about the band structures of metals, semiconductors, and insulators. We talk about the Bloch waves and the K-space, and then how we represent the band structures. So first, students should be able to distinguish the differences in the characteristics of energy bands of metals, semiconductors, and insulators. For metals, as we have learned in the last lecture, they are characterized by having a partially filled band, where the Fermi energy goes through the band somewhere in the middle. And this gives you very high conductivity for these materials. For semiconductors, their band structures are characterized by having the valence band completely filled at 0 Kelvin and the conduction band completely empty at 0 Kelvin, separated by a band gap. The band gap is typically somewhere between half an eV to 3.5 EV. So at 0 Kelvin, it is an insulator. We don't have any free carriers in either of these bands. When you go to somewhat higher temperature, finite temperature, then the top of the valence band may be unfilled. So we have some electrons being promoted to the conduction band that leave some of the states near the top of the valence band unfilled, and then some electrons occupying the bottom states in the conduction band. That give you some finite conductivity, but much, much lower than the conductivity of the metals. For insulators, the band gap will be too high, typically greater than 4 electron volts. That will forbid the promotion of electrons from the valence band to the conduction band. So that gives you 0 electron conductivity. The second student learning outcome is to compare the band gaps of semiconductors and insulators with similar chemistry and same crystal structure. So we're going to use the example of diamond and silicon to compare. They have the same crystal structure, diamond structure, and then the chemistry is similar. They have covalent bonds in between these atoms, but obviously carbon is smaller. The carbon-carbon bond is expected to be stronger than the silicon-silicon bond because the atoms are smaller, so the shared electrons will have more tightly bound to the nuclei in the case of carbon-carbon bond. And this bond strength is related to the separation of the conduction band states and the valence band states. The separation energy, or the band gap, is really related to that interaction for these bonds. So we have a much greater band gap for diamond than silicon. And obviously, the greater band gap will forbid the exchange of electrons, promotion of electrons from the valence band to the conduction band through the thermal generation process. That means the diamond is insulated. So typically, semiconductors have smaller band gap, and insulators will have much greater band gaps. So the next student learning outcome is to describe the general behavior of electronic states in crystals. We know that the electrons are waves. In crystals, they are going to be somewhat close to a plane wave, but not exactly so. So the waves in crystals will retain some plane wave feature, but then the amplitude of that plane wave will be modulated by a function that is periodic, having the same periodicity as a crystal. We call these Bloch waves. So again, these waves are delocalized over the entire crystal. And then obviously, we have a very important parameter describing these waves, that is a wave vector. For a particular wave vector, there may be different states in different bands. So that's why we have this n being the band index. So the probability of electrons appearing in different unit cells should be periodic. That is because the crystal is a periodic system. And this can be shown by looking at the probability distribution from the Bloch wave function. And the energy of those Bloch waves obviously will depend on the K and, of course, the periodic crystal potential, but also depends on the band index. As K is varied through its space, we call K space, then all those states combine to form a band. And for the same wave vector, as I mentioned earlier, there may be multiple energies, so we have multiple bands, and that's why the energy is a function of K, but you may have different bands. So in overall, if you plot the function E versus K, then we have so-called dispersion relationship, and then when you plot it, that's the band structure. So the next student outcome is, how do we represent the band structures typically? We have to involve the concept called Brillouin zones. The energy as a function of K is actually periodic in the K space, and the periodicity is actually given by the so-called reciprocal lattice, which you can form it from the direct lattice or the real lattice. And so with the periodicity, now you can restrict all the Ks to be within one unit cell. to obtain all the information about the EK relationship. And we use the so-called first boron to represent the band structure because that contains all the essential symmetry information that you want to have. And for 1D crystal with lattice constant A, the first boron is really given by this minus pi over A to pi over A. The overall length is pi over 2A, which is the lattice constant in the reciprocal lattice. So typically, this is just one of the examples of the band structure plot in the so-called reduced zone scheme. Basically, you plot all the case within the first boron zone, and then see now this is one band, and you have next band, and you have a third band. So in between these bands, you may be separated by a band gap, but at a given K, you may have energies, multiple energies for states in different bands. But obviously, this is just a very simplified scheme. In a more realistic situation, this is in copper, you see that we have to plot the energy as a function of K in a 3D space, so that obviously is impossible to represent on a 2D paper. So typically people plot the energy as a function of K along some of those high symmetry lines, and then stitch them together to form an entire plot. And in this case, gamma is the origin of the K space, and X, W, L are some of these high symmetry points on the first boron zone of the structure. Actually, this is so-called truncated octahedron. This is a boron zone for a FCC real lattice. And here you show the bands formed by the 3D electrons kind of in the same energy range as the band formed by the 4s electrons. So if you take out the 3D band, you see that's a 4s band only, but the 3D band could actually mixed with the 4s electrons, so because these bands are overlapping in energy. This is the end of the review.